All right, so like I said a minute ago, we're going to start reviewing for the exam two. Exam two, like I said on Wednesday, is about chapters 2 and 3. And what I think would be good to do today would be to look at an important kind of problem and try to emphasize the main themes of chapters 2 and 3 through the context of this problem, okay? And that problem is the context of free fall under the influence of gravity, where you throw a ball or something straight up in the air, it goes up a bit, then comes back down again, hits the ground. We might, for example, be interested in how long does it take to reach its maximum height? What is that maximum height? And how long does it take to hit the ground? And we can think about these things in terms of functions, graphs, and calculus. And we can even start from scratch based on a fundamental model, based on Newton's second law. Newton's second law in equation form is written F equals ma, force equals mass times acceleration. Force in newtons equals mass in kilograms times acceleration in meters per second, which is shorthanded to meters per second squared. That's a law that applies very generally to pretty much everything in the universe that has mass, and a force, some kind of force is being applied to that mass, you know, there's four fundamental, there's four fundamental forces: gravity, electromagnetism, and then there are the nuclear forces, something called the strong nuclear force that I think binds the atoms together, and the weak nuclear force, and I forget what that does. Excuse me, I got a cough here. Colin, is it working? Okay. I am recording it just in case you end up not being able to see. So that would make being in class difficult. I'm sorry about that. How do you apply this to gravity near the Earth's surface? Well, first of all, you have to choose a coordinate system, so to speak. If this is the ground, you have to pick a positive direction. It's natural to pick upwards as the positive direction, say the plus y direction. And you're standing here, and you've got a ball in your hand that you're going to throw straight upward. The force in this context, or right over here, is negative mg, where g is the acceleration due to gravity, and m is still the mass. That's the acceleration due to gravity near the surface of the Earth. And it does have to be near the surface of the Earth. If you go up high enough into the atmosphere, g does get smaller. Near the surface of the Earth, many of you know it's about 9.8 meters per second squared. But I think for the purposes of what I'm showing you here initially, I'm just going to leave it as a g. Because for one thing, if you were on a different planet like Mars, or if you were on the moon, g would be different. It's actually different because those are less massive objects. So g does depend on what planet you happen to be on. Of course, we're all on Earth. It would be slightly smaller if you were at the top of the mountain, of a mountain. So if you go climbing to the top of a mountain, the acceleration due to gravity is slightly smaller up there. What do we want to do with this equation? It's a theoretical model saying how the force and acceleration interact. What do we do with it? Our goal is to figure out the height as a function of time. And as a first step in doing that, we want to figure out the velocity as a function of time. The m's cancel, saying that at least under this model, the mass doesn't matter. You drop a rock, you drop a football, it's going to accelerate at the same rate. Is that exactly right? Actually, it's not right. It's just an approximation. And if you go to the extreme of dropping a feather, of course, it's going to be different for a feather because of air resistance. This model only works close to perfectly, you might say, in a vacuum, though it works pretty well with rocks and balls and that kind of thing. The equality between these two things, G and A, where G is about 9.8 meters per second, I should actually say negative G and A, is what's called a differential equation. And by the way, the negative sign there is necessary if I pick the positive direction to be upward, because that's telling me the force is working in the downward direction. The ball is hanging in the air there, or of course it wouldn't be just hanging if it's traveling upward or downward. Either way, the force due to gravity is in the downward direction, the negative direction, so you need a negative sign to indicate that. Let me write the equation as A equals G. Or excuse me, I wrote the wrong thing again. A equals negative G. This can be rewritten as dv dt equals negative G, where V is the velocity of the ball, the upward velocity. And when I say upward velocity, that means it's positive when the ball is traveling upward, when you first throw it upward. And the velocity is actually negative when the ball is traveling downward. The sign, plus or minus, keeps track of the direction. Y is positive when the ball is above the ground, and negative if the ball goes below the ground. Like if you dug a hole and the ball fell in the hole, then Y would become negative. Y equals 0 is right here at ground level. V is positive when the ball travels upward and negative when the ball travels downward. The acceleration, which is the rate of change, derivative, that's a derivative of the velocity, in this context is always negative. It's a negative constant, negative G, about negative 9.8 meters per second squared. So how does this help us? We're looking for the velocity first as a function of time, and I say it equals a negative constant. I need to find a function whose derivative is that negative constant. I hope you could guess the answer. I mean, if you want to pretend it's 9.8 there, you could, if this was a negative 9.8, an antiderivative of this would be negative 9.8 times t plus an arbitrary constant c. So this is now, right now, a review of indefinite integrals. I could take this equation and I could write it in this form. V equals the integral of negative g dt, where negative g is a constant. Go ahead and pretend it's negative 9.8 if you like, but I want to allow for it to not be perhaps here, to allow for me to think about this, say, on the moon or on Mars or something. That's a constant. When you integrate a constant, you get that constant times the independent variable. It's just like saying the integral of 7 dt is 7t plus an arbitrary constant. I should go plus c. So t here is indeed the independent variable. T is time in seconds, and that is the independent variable in all of this. Why does this indefinite integral equal this? Because if you differentiate this, you'll get the function just to the right of the integral sign. This is because the derivative of the function on the right with respect to t. C is a constant, negative g is a constant. That derivative is just going to be negative g. Negative 9.8 if you like. That's what indefinite integrals mean. And even though I haven't assigned homework problems with this symbol, I have talked about it. Well, you know, a couple weeks ago I talked about it, and I'm talking about it again now. I want you to know the basics of what this symbolism means. As another example, the indefinite integral of cosine of t dt is sine of t plus c, since the derivative of sine of t plus c is cosine of t, the function right there. Whatever function is to the right of this integral sign, this kind of elongated s, is the function you're integrating, and whatever answer you get when you differentiate it, it better equal whatever's right there. The dt just says I'm integrating with respect to t. You might wonder, why is there a d in there? I'll explain that when we get to chapter 5. But is this c truly arbitrary? I mean, yes, for any number c, this derivative will be true right here. But for the particular situation of throwing the ball up, is c truly arbitrary? No. C is going to be something specific. It's going to be the initial velocity, in fact. You might call it v sub 0. If we assume v at time 0, the velocity at time 0, this is a bit of an abuse of notation. By writing v of 0 like this, I'm treating v as both a variable and a function name. That's a common thing to do in science. In math classes, we try to be a little bit more careful and maybe use some other letter like F or G or H. But in science, you'll often see a variable like a velocity v and say, well, v is both the dependent variable and it's the function name. The main thing is just don't let it bother you. It's sloppy notation, but just don't let it bother you. It used to bother me, so that's why I'm telling you this. Assume this is something fixed, call it v sub 0, or v naught for short. Not as an NOT or KNOT, but not v naught as in NAUGHT is sort of a synonym for 0. V sub 0 or v naught for short is the initial velocity. I'm pretending that's a fixed number. You could pretend it's 20 meters per second. You throw it straight upward at 20 meters per second. Or maybe you think you can throw it a lot faster. Maybe you think you could throw it 40 meters per second. I am talking about straight up and down motion here. This stuff could apply if I throw it more typically along some path that's a parabolic path. I could still think about these things for the height. That would still be valid, because kind of the height and distance traveled horizontally are independent of each other in the absence of air resistance. But I'm just trying to keep things simple here. That C cannot be anything. Then I can solve for C in terms of V naught. I can go back up here to this function and replace T with 0. Get negative G times 0 plus C. By the way, did decide that for today and Monday, we're not going to bother with the class participation. And then after the test next Wednesday, I'll probably have you poll whether you want to continue with class participation or not. Friday of next week, I'll do some sort of poll. Okay. But today and Monday, we won't worry about it. But it probably would be good to take notes anyway, as many of you are. Well, negative G times 0 is 0, and 0 plus C is C. So C must be V0. C can't be anything. It's got to be something fixed, something in particular related to the physical situation. It's got to be the initial velocity. So you can now write your velocity. You'll sometimes see this kind of notation, V equals V of t. That's again abusing notation. I'm okay if you just write a V. I'm also okay if you just write a V of t. It doesn't matter to me. And technically, again, this is not good, but it's something scientists do. So we'll go ahead and do it. It is negative g times t plus V sub 0 or V naught. So that's how the velocity depends on time. What have I emphasized so far? I've emphasized, well, a physical model. I've also emphasized that the acceleration is the derivative of the velocity. The rate of change, the instantaneous rate of change of the velocity. That's what the acceleration is by definition. Intuitively, we think of acceleration as speeding up. Though keep in mind, you got to be careful here when you're thinking about velocity and directional motion. If you throw the ball straight upward, it slows down as it goes upward, but actually its acceleration is still negative 9.8 meters per second squared. The fact that it's slowing down as you travel in the positive direction means it's got a negative acceleration, not a zero acceleration, a negative acceleration. And it's slowing down, but on the other hand, if it's going downward and it speeds up, the acceleration is still negative because it's in the downward direction. It's still negative 9.8 meters per second squared. So a negative acceleration will slow you down if you're traveling in the positive direction, but speed you up if you're traveling in the negative direction. So you got to be careful when you think about that. Before we go on to the height as a function of time, what could we do with this? We could, for example, use this to figure out when the ball reaches the peak, the highest point. What should I do? If you've been in physics, you've done this kind of thing before. To find the time of maximum height for time, call it t sub max, if you like, of maximum height. What should I do? What algebra should I do? Solve for t when what? When v is 0. It's going to be at its high point the instant in time when the velocity is 0. As it goes upward, the velocity is positive. It is getting closer to 0 as it slows down. That instant that it's at the peak, that's where the velocity is 0. And then one instant later, it's going down and its velocity is negative and becomes more and more negative as it continues to fall. So we set v equal to 0 and solve for t. So that's an algebra skill. Set v equal to 0. 0 equals v of t equals negative gt plus v sub 0, and solve for t. Do your algebra steps. Add g of t, g times t to both sides, you get gt equals v0. Divide both sides by g and you get t max, if you want to go ahead and call it that. I didn't call it that along the way here, but I could have. T max is v0 divided by g. So the time to reach the maximum height is that. So for example, if you were strong enough to throw the ball straight up at 40 meters per second, the time it's going to take before it reaches the peak and starts coming back down would be 40 divided by 9.8, a little over 4 seconds. Yeah, that's pretty fast, actually. You'd have to throw it pretty hard for it to keep going up for a little over 4 seconds. I don't know that I could do it. Usually when you're throwing the ball upward, it's going to reach its peak in maybe 2 or 3 seconds, typically, I think. Remember that I said a quantity, whether it's a constant or a variable, is all in your head. It's all in how you're thinking about it. That's what I want to emphasize right now. I've been thinking of V0 and G as constant, but I could decide to think of them as variables. And I could think of this as a function of both V0 and G. I could think of it as a multivariable calculus function. I could say let f of G comma V0 equal V0 over G. A multivariable calculus function. There's 2 independent variables. If I just change my perspective, if I decide I want to view the initial velocity as a variable and G is a variable. Wait, why would I do such a thing? I mean, after all, you're on the Earth's surface, G is 9.8, and you are going to throw it with some initial velocity. Why think of it as a variable? Because it could provide insight into what happens if you change either quantity a little bit. If we think about it with calculus and derivatives and linear approximations, which is what I'm about to do. If you change the initial velocity a little bit, or if you change G a little bit, like if you went to the top of a mountain, or more extreme, you went to Mars. I could think of these as variables, and I can find their derivatives. And this does equal tmax, so I'll go ahead and write that here. I could find it, and there's a function of more than one variable. I could find a partial derivative of tmax with respect to V0, for example. The derivative of tmax with respect to V0. I'm using the curvy partial notation, sort of like a curvy D. To tell you the truth, I don't care on the test if you feel like just using a regular D, it's fine. Feels almost magical to use a curvy D. Like, why did we do that? Well, it's just to remind ourselves that this really depends on more than one variable. That's all it's for. And it's kind of fun to make, so we go ahead and do it. What do I do to do this? I treat the G as a constant. That's what I do, and differentiate with respect to V0. This is like a variable over a constant. It's like x over 5 or x over 9.8. What's the derivative of x divided by 9.8? Do I need the quotient rule? It is, after all, a quotient. I claim no, you don't. Why can I get away with not using the quotient rule here? Because G is a constant, and dividing by G is the same as multiplying by the constant 1 over G. If G were 10, which it would be, by the way, if we dug a tunnel down a couple miles below the ground level or something. If G were 10, this would be 1/10. A constant times, say, x would be, the derivative would just be 1/10. The derivative here is just 1 over G. What about the derivative of tmax with respect to G? Think of G as a variable and think of V0 as fixed. There I could use the quotient rule, the variables in the bottom, but I don't have to. I could think of this also as being V0 times G to the -1 power and differentiate that with respect to G. Think of the V0 as fixed. You just bring the -1 down in front. It's just the power rule here. So you get a negative sign in front, V0 G to the -2. This derivative is going to be negative V0 G to the -2, or if you prefer, negative V0 over G squared. What good is this? Well, one thing it's good for is making approximations again if you change V0 and G a little bit. Let's plug in some numbers now, some particular numbers. So let's go ahead and use G equals 9.8 when we think of G as fixed. And let's let V0 be something when we think of V0 as fixed. Well, maybe we should go ahead and think of V0 as fixed as well. So let's say G is 9.8, and you don't have the negative sign there because the negative sign was already taken care of in the model. G itself is a positive number. Negative G in this context is the acceleration due to gravity. It's got to have the negative sign, but G itself is a positive number. So let's take G to be 9.8, and let's take V0 to be, oh, maybe I could manage 20 meters per second if I did it. So suppose this is true. What can I do with this information? I could, for example, figure out how long it's going to take to reach the maximum height. Then tmax, by this equation right here, it's going to be V0 divided by G, 20 divided by 9.8, a little bit bigger than 2. 20 divided by 9.8, about 2.04. I'll go ahead and round it to 2.0408. That's probably too many significant figures, but I'm not going to worry about it. It's going to take about that long to reach the maximum height. What can I now do with these derivatives? I could use them to predict how long it's going to take to reach the maximum height if I change V0 a little bit, or if I change G a little bit. Or maybe even if I change them both, but let's just do it one at a time. What is tmax if, say, V0 changes from 20 meters per second to 20.03 meters per second? i.e., delta V0 is 0.3 meters per second, the change in the initial velocity. Which, of course, in any one time you try throwing the ball, you can't do. But then you say, okay, I'm going to try throwing the ball again, and I'm going to try to throw it a little bit faster. And you do throw it a little bit faster by 0.3 meters per second. This is really key. Make sure you're paying attention here. This is linear approximation we're about to use. The notation is getting a bit hairy. I could call it T sub max nu. The new T max, the new time to the height. Double subscripts there, double labels. I'm running into this issue because I'm avoiding function notation, but is approximately Tmax old, that's the 2.0408, plus the rate of change, the derivative of Tmax, with respect to what? We're changing V0. It's got to be with respect to V0. Evaluated at G comma V0 equals 9.8 comma 20 times the change in V0. Now that's a very complicated looking equation, but conceptually it's no different than what we've been doing. Take the initial value, add on the change, the approximate change that comes from taking the rate of change times the change in the independent variable. And here again, I'm thinking of V0 as being the independent variable. We can plug numbers in now. Tmax old is this thing. This thing is Tmax old. 2.0408 plus what was the derivative that we got? Well, I guess we haven't evaluated that yet. I've got to use this equation right there, 1 over G. 1 over 9.8 times the change in V0 is 0.3. Hang with me here. Do this calculation. 0.3 divided by 9.8. This is about 0.0306122. If I add that to 2.0408, I get about 2.0714 as the new time to reach the maximum. I increased my initial velocity by 0.3, and my time to reach the maximum went up by a little bit, by 0.03 seconds. Is this right? How good is this approximation? We didn't actually have to do the approximation. We could have used the original equation. We could have used this equation again when V0 is 20.3. Watch what happens. Watch where I'm pointing. Do 20.3 divided by 9.8. My prediction is that we should get about 2.07. I'm not so confident that we'll get 1.4. We did. How about that? 2.0714. So I made a prediction of approximately what the answer would be using a derivative, and I confirmed that the answer was pretty good using the original function. You might wonder, only have 1 minute, but don't put things away yet. You might wonder, what's the use of this? I mean, why can't I just always use the original function? Certainly pretty obvious that you can use the original function, and this, even if this were a more complicated equation, we could still use technology with the original function. So why not just do that? A few different answers you could give. One is that linear approximation can still give insight into the behavior of functions. That's not clear how that's the case here, but it can. A second reason is that it does give you insight into the nature of the meaning of calculus and derivatives as rates of change. And a third reason is it's actually more useful than you might imagine, especially when you get into a differential equations class, if you ever take that class, which many of you will. The idea of linear approximation really pays dividends in differential equations. Okay? So that was kind of a high-level thing here that I did, but it did emphasize derivatives and antiderivatives, indefinite integrals, emphasize problem solving, and emphasizes multivariable calculus, partial derivatives, and rates of change, in other words, linear approximations. On Monday, we'll do a more step-by-step review of all the topics we've covered instead of the context of an application. All right, see you then.